Alrighty, let me share my screen. Okay, perfect. So today I'm going to be going over lecture 25, which was all about your phase diagrams. It can be found in section 6.5 of your textbook. So first we're going to start off with the definition. What is a phase diagram? From your textbook, it's defined as a graphical representation of the dependence of the stabilities of the physical states of a substance on temperature and pressure. It's kind of a hefty definition, so I'm actually going to break it down a little further so we can really get to understand each part of it, and then we can put it all together and dive into phase diagrams. So first, we have your physical states. You have three physical states. You have your solids, your liquids, and your gases. You can see them in the picture up here. What determines the physical state of a particle? That would be your kinetic energy and your intermolecular forces. It's really a balance between these two, and as the balance between them changes and shifts, so does the substance. It can become a solid, a liquid, or a gas. So kinetic energy is what keeps the molecules apart and keeps them moving around. It's a function of the temperature of the substance, which I will talk about in a little bit. Then you have your intermolecular forces. Those are attractive forces that try to draw the particles together. So just kind of a little more about kinetic energy. Up here we have your gases, your liquids, and then your solids. So we said kinetic energy is what keeps those molecules apart and keeps them moving around. So obviously the gases right here, the molecules seem to be having the most movement. So that means it would have the most kinetic energy. Then it would be liquid. It has some movement, but not quite as much as gas, but it has more than solid. And then solid would have the least amount of kinetic energy. One thing that's important to remember is that although it looks like they're standing still, solid is still moving. It's just a lot less movement, and so it's not as noticeable. But solid, the molecules and particles, they do still have movement to them. Perfect. So there are kind of three factors that affect your physical states and help change from physical states. You have your intermolecular interactions, then your temperature, and then your pressure. So the intermolecular interactions will be a constant. Generally, they don't change. That's because they're the intermolecular bonds, and those typically don't change. However, the temperature and pressure, they are a changing factor. And when you pair them with the intermolecular interaction, you'll see a change in the physical state of your substance. So then you have, like we said, you have your temperature. And as the temperature changes, it affects the particle's energy, which then affects the kinetic energy. So that's important to remember. Temperature has to influence the kinetic energy. So let me give you an example of this to kind of explain it better. So as we begin to heat a substance, let's say we have a solid. You're going to start heating your solid, and it goes, as you heat it, it's going to become a higher temperature. As it's gaining heat, becoming a higher temperature, you're gaining more energy, and then you keep gaining energy until the kinetic energy will eventually exceed the energy of the intermolecular forces that holds those particles rigidly in place. So again, you have a solid. The intermolecular forces are holding that solid pretty rigidly in place. But as you begin adding heat to that solid, you're changing the temperature, which is gaining more energy, which is increasing the kinetic energy. So the kinetic energy is going to exceed beyond the intermolecular forces, so they're no longer balanced. Because of this change, you're going to see a change in your physical state of your substance, and that solid should melt and start becoming a liquid. Then you have pressure. Your pressure is what affects your intermolecular interactions. Pressure is actually defined as the ratio of force to surface area. So how does that all fit in with the physical state? Well, think of it this way: as you begin to increase the pressure on a substance, it keeps that substance from expanding. So it's going to push those particles together. So this pushing of molecules together is going to increase the strength of intermolecular forces because, again, you're increasing the pressure. So you're decreasing the space they have. It's bringing them closer together, and you're pushing those molecules together, which means they're closer together, which means the strength of the intermolecular forces is going to be stronger because they're closer together. Same thing for the opposite. The less pressure you have, the more molecules have to spread apart. So you're increasing the distance, which means the strength of those intermolecular forces is going to be weaker because they're further apart. Let's see. Next, we have this chart. This is pretty familiar. It did come from other chapters throughout the year. It's really important. Dr. Mortensen really wants us to understand the direction and flow because this shows the changes in physical states. So I'll just kind of go over it quickly. So as we increase the temperature, we just talked about this, we're increasing the kinetic energy, which changes the state by melting, vaporization, or sublimation. So you have those right here. You have your sublimation, vaporization, and melting. And those are all from an increase in temperature. Okay. Next we have you have a decrease in your temperature or a decrease in kinetic energy, and you begin to change your state through either condensation, deposition, or freezing. It's important to know kind of like, okay, so liquid to a gas, that's vaporization. Solid to a gas, sublimation. Solid to liquid, it's melting. Same thing, gas to liquid, condensation. Liquid to solid is freezing. And then a gas to solid is deposition. So just kind of know the direction and flow of those, as well as kind of you're adding temperature, so you're gonna increase the kinetic energy, etc. And then one thing to note, you have pressure, which changes the intermolecular interactions or distance between your molecules. And this increase can cause the substance to condense. So pressure has an effect on your condensation. All right, so now that we've kind of reviewed physical states, gone over those a little bit, we're going to dive right into phase diagrams. I'm just going to pull this up. This is the definition of a phase diagram. It's a graphical representation of the dependence of the stabilities of the physical states of a substance on temperature and pressure. Perfect. So this right here is what a phase diagram looks like. First, I'm going to just kind of go over the basic features you should be familiar with. Right here on the y-axis, you have your pressure. The x-axis, you have your temperature. Okay, and then within the diagram, you have your solids, you have liquids, and then you have your gas. Those are the three physical states that we talked about. And then one thing to note is that you have three main lines on your phase diagram. So you have one right here, and one right here. And they're kind of dividing the different phases. But what those lines actually mean, it's a combination of temperature and pressure at which the two phases on both sides of each line coexist in equilibrium. So these lines, simple equilibrium, just remember that. Those lines mean equilibrium. And then I think I'll talk about it a little bit later, but I just wanted to kind of show you that these lines also separate the phase changes. So for example, this line right here, it's separating this one right here. It's separating your solids from your liquids, and that represents either melting or freezing. Obviously, if you're going from a solid to a liquid, that's going to be melting. If you're going this direction from a liquid to a solid, that's freezing. Same thing with this line, it's separating your liquids and your gases. And so that's going to represent a series of either boiling or condensation. Again, depends on the direction you're going and the pressure and temperature. And then lastly, you have this line down here, which actually separates your solids from your gases. And that's going to represent a series of sublimation or deposition. Again, it's going to depend on the direction you're going. The temperature and pressure will kind of determine that. And we'll talk about that a little later as well. Okay, another feature you're going to need to know is called the triple point. And this point is marked by a B right here. And this point is where all three states of a substance exist simultaneously at this exact temperature and pressure. I'm not sure if you actually need to know this for the test, but this is just good to know. The triple point of water has a pressure of 0.6 and a temperature of 0.01 degrees Celsius. So you can see right here, you have your pressure of pressure of 0.6 comes right here, and it meets up with the temperature of 0.01. And that's your triple point. And again, that's where all three states of your substance can exist simultaneously. All right, next we have your critical point, and that one's actually going to be up here. It's marked by C. This critical point is the specific temperature and pressure where the liquid and the gas, so you have your liquid and your gas, they're going to have the same density and they'll become indistinguishable from another. And it's also important to know that this is where the two states, it's important to remember that this is where the equilibrium line ends. So it does get cut off right here, and the two states become indistinguishable beyond. This point is actually reached because thermal expansion at high temperature decreases the density of the liquid state, while high pressure compresses that gas into a small volume, which increases its density. All right, and so beyond that critical point, remember this is your critical point right here, and the critical point marks the end of that equilibrium line. But beyond that is where you have your supercritical fluid. This is a substance in a state that is above the temperature and pressure at the critical point, as you can see, and it's where the liquid and the gas phases are indistinguishable. Just some characteristics of the supercritical fluid. It has an ultra-low viscosity of a gas. It can easily diffuse through solids, and it can dissolve substances. Just some fun facts about it as well. Supercritical CO2 is often used in food processing, and so they use it to decaffeinate coffee beans and remove fat from potato chips. It's also used to extract essential oils from plants and is used to make perfumes and to dry clean clothes. So kind of fun facts about that. Alrighty, so we have two phase diagrams, but there is actually a difference between these two. So I'll kind of let you look over that for a second, and then we'll talk about where the difference lies between these two phase diagrams. So the difference is actually going to lie in this line right here and this line right here. If you'll notice, one has a positive slope and one has a negative slope. This is the solid liquid line on both of them. And again, one has a positive slope, one has a negative slope. So why is there a difference? So first we're going to talk about the positive slope. That was that first one. As you can see, the positive slope results from the solid phase having a higher density than the liquid. Generally, for most of your phase diagrams, they will have a positive slope. It's a pretty typical thing to see. So the positive slope is as you're increasing in pressure, you're increasing the melting temperature. So that's important to remember. Next, we have that negative slope. This is the one exception. Like I said, most of the phase diagrams are going to have a positive slope, unless it's a phase diagram for water. This is the one exception. Water has a negative slope. Water is an anomalous. Basically, it just means it's the exception because it has that negative slope. So it slopes left because the liquid phase is actually more dense than the solid phase. If you remember from the previous slide, it's obviously opposite, which is why one is positive, one is negative. So a way to kind of remember why this is, think of ice and water. Ice is lower density than liquid water, unlike most other substances which typically have denser solid phases. But again, remember, water has that negative slope because the liquid phase is going to be more dense than the solid phase. Okay, perfect. So this is a really good chart. I like this one because it's pretty clean and organized, and it's a good way to practice reading your phase diagrams, which is important to know how to do. So we'll just kind of review what we talked about. So point A right here, this is going to be your triple point. Then you have your critical point at point B. Beyond the critical point, you have your supercritical fluid. You have your solids right here, your liquids right here, your gases right here. Along the x-axis, you have your temperature. The y-axis is your pressure. Again, you have these lines right here. And just to review, these lines represent equilibrium. So you have the line sharing liquid and gas right here, the line for solid and liquid right here, the line for solid and gas right here. And again, this is all equilibrium. That's what those lines mean. And then let me clear all of that. The reason why I like this one is because this shows the direction and where the melting and freezing is, vaporization and condensation, sublimation and deposition. So it's just important to remember where the triple point, critical point are, and it's also important to know where the solid, liquid, and gas lie. One way to remember which area corresponds to each of these states is to remember that the conditions of the temperature and pressure that are most likely to be associated with a solid, a liquid, and a gas. So let me kind of explain what I mean by that. So a low temperature and a high pressure are going to favor a solid. So again, you have your low temp. Sorry for the horrible drawing. And then you're going to have a high pressure of a solid. And that makes sense because your solid is right here. It's on the lower end of the temperature, but it also goes up more, so it's going to use more pressure. Gases, on the other hand, are most likely to be found at the higher temperatures, which we can see. That's why it's taking up most of the bottom of the diagram, and then it's going to be found at lower pressures. So just kind of think of it in relation to that. So because your gases require higher temperatures, it's going to be more on the right side, but they require low pressures, so it's going to be on that bottom portion of the diagram. And then you have your liquids, which kind of lie in between these extremes. So really, if you just remember one or the other, if you just kind of think of, okay, solids, those require a low temperature but a high pressure. So look at your chart. Where are the lower temperatures? Where's the higher pressure? And you can place it pretty easily. So that's kind of a good way to remember which portion belongs to each physical state. Okay, perfect. So I just have a couple quiz questions. We will just go over them really quickly, and then I'll give you the answers and kind of talk about why it is. So the first one is pretty simple. A phase diagram shows the relationship between A, pressure, volume, and the three phases of matter, B, temperature, pressure, and the three phases of matter, or C, temperature, volume, and the three phases of matter. So kind of think back to the phase diagram. Maybe something that would be helpful would just be kind of like sketch it out and just quickly label it and kind of place what's on the x-axis, what's on the y-axis. So the answer to this one is going to be B. It's going to have the temperature, pressure, and the three phases of matter. So I'll just sketch it out really quickly. If you remember, you have your temperature. That's going to be going this way on the x-axis. You have your pressure going this way, that's on the y-axis. And then you have your three phases, and generally it's kind of divided like this. And then if you remember, you have your solids right here. You have your liquids and your gases. And again, the way I remembered that is that your solids typically utilize low temperatures but high pressure. And then your gases are going to utilize high temperature but low pressure. And then your liquids just kind of sit in the middle. They just are in between that. Perfect. So the next one, The question is down here. So at 1.0 atmosphere pressure and 150 degrees Celsius, what is the phase of water? Is it a gas, a liquid, or a solid? Perfect. So the answer is going to be gas. And the way to do this is you find, okay, so I have 1 atmosphere of pressure and 150 degrees Celsius. So I'm going to go up here and find 1 atmosphere of pressure. 150 degrees Celsius is not labeled, but you don't really need it because you can see, okay, this is 100, so it's probably somewhere like right here. I don't know, just eyeball it. And then all you're going to do is you're going to draw a line out from your pressure until it reaches to the temperature right here. And then you draw a dot. And then you look and you say, okay, that's in the gas phase. So it's pretty simple. It's just, again, knowing how to read the diagram and how to use that. All right, and then our last question. On a phase diagram, the temperature and pressure at which the phase boundary between the liquid and the gas ceases to exist is called the A critical point, B boiling point, and C triple point. So kind of, again, think back and start kind of drawing it out or just visualizing it in your head, labeling each point, where each of the phases are. And so we are looking for the phase boundary between the liquid and the gas and where it ceases to exist. Perfect. That is actually going to be your critical point. Again, if you remember, we have your phase diagram, looks something like this. Ooh, that was pretty bad. But you have your solids, your liquids, and your gases. And actually, I'm going to redraw that. That was pretty bad. Okay, so your phase diagram. You have this coming up here, and this coming up here. And then you have your solids, your liquids, and your gas. Okay, so we're looking for the phase boundary between the liquid and the gas and where it ceases to exist. So that's going to be, if you remember, right here, because again, this is the boundary between solid and liquid, and where it ceases to exist is your critical point, and kind of a, yeah, it's just important to remember that that's where it stops. So that's pretty much all I have. I hope that was helpful, and that's all.